Oh, so Daria said that there was supposed to be spring, but if you want a place for the next, better place for the next edition of .NET Summit, come to Italy. Because it's a wonderful country in which you can go from -10 to 20 in just 1 week. Last week, this week actually, was -10 Monday, will be 20 tomorrow when I'm back home. And so all those degrees in a week. But speaking of technology, where we could be in, well, not a week, but I would say in 5 years, who knows? And quantum computing is one of the most fascinating things we can expect, maybe not in 5 years, probably in a much longer term, in 20, let's say 20 years from now, to be, part of our life. So it's, because I see a lot of dummies, extremely curious, let's try to take an approach to, dummies approach to quantum computing. You may have heard that Microsoft, Google, the big IBM, the big guys are talking a lot, are posting a lot of material on quantum computing. There are some announcements of prototypes. Nobody really knows what it is. But from my perspective, regardless of Visual Studio extensions for quantum computing, Q#, whatever it is, sounds to me pretty much, ridiculous. I mean, it cannot be really, really serious from the perspective of developers. Because the first question I asked when I heard about Q# was, okay, how can I write hello world in Q#? Which is a completely different problem, because quantum computing is, I don't know what it is. And I'm not alone, because this is a wonderful quote. If you think you understand quantum mechanics, quantum physics, which is the foundation of quantum computing, well, you don't understand quantum mechanics. Like the Schrödinger cat, it's live and dead at the same time. So you understand and you don't understand at the same time. But the guy who said that is not me. It's not any anonymous person on Twitter. It was Richard Feynman. He's known to have been one of the best teachers, Nobel Prize for physics, one of the fathers of the idea of moving towards something else based on quantum physics, the computing model, the conventional computing model we work with today. In our world, we know that we live in a world that is our world of computing is a world discrete. It's not continuous, is limited, and not unlimited. So we face usually, as developers, as modelers of solutions, a sort of a gap between what we see, what we perceive around us, the world in which we live, which is a world inspired by the laws of mathematics, laws of physics, and everything is continuous. There is the concept of infinite. But when we try to take those things we observe in software, so when we move from the world in which we live to the world in which we code, we have to create models, approximations. And we have to essentially move from the world of continuous to the world of discrete. Numerical analysis is a branch of computer science that deals with that. I mean, I was kind of shocked in 85, 6, 7, I don't know, many years ago, when I took that exam at university with the idea that, okay, you have to cut at some point your calculations, you have to produce a number, and you don't want to know what you are going to lose. So physically, computers tend to have a internal, in the folds of their kernel implementations, they have tables in which they don't even do calculations. Sometimes they just take numbers because they know what it means to do what it means, what in Minsk. Nice. To use this as a slogan. Free for you. What in Minsk to be a developer. Anyway, the problem we face is mapping what is continuous to what is discrete. This is the challenge of the computing model, and as smart humans, we do that. And we are very smart in what we flexibly do to deal with discreteness and limitations. Okay, the computing model of today is based on this kind of thing. In a clip art, a transistor. Transistors can be considered atoms, like atoms of the computing world. There are real atoms, so physics say, in the world in which we live. There are transistors as atoms in the world of computing. Consider that in a 1 gigabyte USB stick, we have 1 billion, 73 million, and whatever, bytes. But a byte is 8 bits. So we have over 8 billion transistors in the area of a fingernail, more or less. Dimensions of transistors have never been the same over the years. Before the Second World War, around the 40s, when people like John von Neumann, Alan Turing, and many others were laying out the grounds of the world, the conventional today's world of computing. At that time, the dimension of a transistor was was in the order of magnitude of a micrometer, 10 to the power of -6, a millionth of a meter. 2016, today they are still a little bit smaller, but not that much. The order of magnitude is the same as 10 times nanometer, so a billionth of a meter. But there are estimations that only a couple of years from now, 2020, which is, 2020, no, it's 2 years from now, actually. It could be around 7 nanometers. Now, 7 nanometers is a very critical number. You say, okay, today we are around 10 nanometers. So 10 nanometers, 7 nanometers. So we are talking about 3 billionth of a meter. Does it really make a difference? It makes a huge difference. This is the problem. It makes a really huge difference. And because it's on the border of the level that physics has established to be what is macroscopic and what is microscopic, what is atomic and what is subatomic, what is ruled by the laws of conventional physics and what is ruled by the law of quantum physics. That's it. 7 nanometers, and we're there, almost there. Interestingly, this is a scale. 1 meter, 10 to the power of 0, 1 centimeter, 1 millimeter, 1 micrometer, 1 nanometer, an atom. So it's there. It's 1 order of magnitude. Atoms. I mean, we are made of atoms. And the transistor is really close to that. 1 order of magnitude is huge space. Much bigger than space here. Nice. Anyway, 1 order of magnitude is a lot. But, we are that's crazy. We are really there, really close to there, and we are approaching. If you don't trust me, I think that is 1.1 10 to the power of -10 is the size of an atom of carbon. So, a few other numbers. 10 nanometers is the current size of mass-produced transistors. And it's only 14 times wider than a DNA molecule. We're talking about the things we are made of. We are made of transistors. That's wonderful. I'm reading, by the way, I'm reading these days a book from a Portuguese author. All Portuguese people have just combinatorial formula of the same names, so João dos Santos Rodrigues or something like that. I'm unable to repeat the name of this guy. The book is called The Einstein Prophecy, or Einstein Enigma, whatever it is. But within this book, there are so many, conversations between a father and a son about cosmology, about the beginning of the world, about the role of physics, about quantum physics. And the funny thing is that at some point, the father explains to the son the difference between humans and computers, and he really go close to the point of saying humans are made of atoms, computers are made of transistors, but there's no difference at all. At some point, so if you take this to the limit, there is no difference at all. It's only a matter of computing power. The moment in which the technology will allow us to put into the computer the same power of humans' neural networks, well, there is no reason why computers could not have emotions. Wow. This is absolutely fascinating, because it's true. I always thought about that. So I only found in that book words that expressed thoughts, ideas that I always had in my mind. And I discussed this many, many times on a beach. Yes, with a drink on a beach with my son. So 14 times transistors, 14 times wider than a DNA molecule is really proving that at some point computers could be made similar to atoms anyway. Anyway, 17 atoms of silicon to make today a transistor with the size a transistor has for mass-produced chips. You should be familiar, or you may have heard this sentence: the number of transistors incorporated in a chip will approximately double every 24 months. This is Gordon Moore, the Moore law. Gordon Moore, founder, one of the two founders of Intel Corporation. So we are very, very, very close to the limit of how small we can make transistors. 7 nanometers. We are not there yet, but we are fastly approaching. Nobody can really honestly tell how fast we could go there. So if it really takes 2 years or more, because we are really, I mean, it's just like with telephone lines. You can take wires for kilometers, and then the last mile is the most problematic. So we are in the last mile, probably, of changing the computing model. So the reason why 7 nanometers for the transistor size is problematic is that technically today we could create transistors with that size with silicon. There are prototypes even much smaller than that. There is it was built last in 2017 at Berkeley, 1 nanometer transistor, not made of silicon, made of molybdenum disulfide. I don't know what it is, but I assume it exists. It's some valid material. I'm not expert in chemistry. Anyway, molybdenum sounds familiar, but I don't know what it is, but it sounds familiar. I heard that name maybe in some memories of when I was in high school. So the problem is quantum tunneling. I said that 7 nanometers is the border between macroscopic and microscopic, and when you cross the border and you get into the world of ruled by the laws of quantum physics, the thing the effect we experience that is challenging for building a realistic quantum computing hardware is called quantum tunneling. Now, what is quantum tunneling? How can we explain easily? We always lived, macroscopically speaking, in a world in which sometimes things are, either white or black. Outside is white, total white experience because of the snow. Inside is, let's say, black. Black, white, on, off, in, out, bits, atoms of information. Quite simply, this stops being a fact when we cross the border. So on this side, imagine that this is the border. Here, either 0 or 1. Here, it could be 0, 1, or both, or whatever else. That's it. This is the problem. Now, technically, this is a representation of a transistor. A transistor is usually has a base of some conducting material, typically silicon. So imagine that the thing here is a plane of silicon, and there are three parts: source, drain, and a gate in the middle. The gate is the critical part. Now, the size of the gate is, at the moment, 14 nanometers. And if the silicon area is made of electrons freely moving. So if there is nothing applied to the gate, electrons flow. So underneath the gate, there are electrons, and that is interpreted as a value of 1. The moment in which we apply, so this is the physics of transistors, some electricity to the gate, the effect is that electrons don't like each other, so they get power here. They don't like it, and they stay away. So underneath the gate, there is no presence of electrons. It is interpreted as a value of 0. I'm cutting a long story short. Now, when we reduce the size of the gate to less than 7 nanometers, electrons start behaving in a funny way. They have statistically the likelihood to pass the barrier. So we have heard that charges of the same type tend to stay away. Not necessarily. So the likelihood that they decided to be homosexual, so to speak, the chance we have homosexual electrons in quantum physics is not 0. So we can find 2 electrons of the same size that love each other, and they just go here. So the chance that we have underneath the gate, we can have electrons or not. It depends. So value of what? This is quantum tunneling. This has brought to the introduction of the concept of a qubit compared to the bit. The bit is what we know, 0 or 1. Qubit is 0 or 1, but also both 0 and 1 at the same time. In other words, a qubit may be in multiple states at the same time. Unbelievable? Well, also Einstein said that, nah, bullshit. Essentially, Einstein said that. But actually, the funny thing is that Einstein was proven wrong. I mean, there's a lot of literature, wonderful literature, about discussions, conversations between Niels Bohr, one of the recognized fathers of the quantum physics, and Einstein. And there is, I found recently documentation about the conversation they had in a meeting, and Einstein went there and said, "You, Bohr, you and all your Copenhagen team are saying a lot of bullshit because of this. And Niels Bohr thought, no. Apparently, Einstein was right. But after 2 nights of endless work, Bohr was able to prove Einstein wrong. Using the same foundation of the relativity theory. That's fantastic. It's a wonderful story. So apparently, as absurd as it may sound, quantum physics explains how things really work. So, under a given size that we can take to the number of 7 nanometers, so in that small world, in that nano world, an atom can be in multiple states at the same time. This is, how is it possible? This is called superposition. This is the name of the quantum physics theory that explains that. It's called a superposition. I have a computer science degree, and I had a hard time getting my exams done, my 2 exams done of physics, so I'm not really an expert in this area, but I try to understand things. So apparently, okay, my son validated this slide, right? So my son is studying math, is fresh in his skills on physics and mathematics. So light is made of photons. A photon is a particular particle that at the same time is a wave and a particle. So it's 2 things at the same time. So as a particle, it cannot physically trespass barriers, but as a wave, it can. This is the fact that has been observed. So superposition can be described as when 2 waves add together, sum up together to make a third one that is function of both the original. So imagine, so in a quantum computer, we can have photons. So I'm talking about in the hardware implementation. Okay, we can have typically we have photons. Okay, that 0 and 1, so to speak, that behave like a wave, and they can sum up together. So in other words, the point of superposition here is that the possible states, 0, 1, but even 0, 1, 2, 3, 4, 5, whatever it is, any number of possible default values that can be assigned to a qubit, also generate any linear combination of those. So we are developers, right? Enum types in .NET. When you use the flags attribute on enum types, it means that valid value for that enum type are any value explicitly listed, but also any combination of values. This is the same as I found a much better way to explain superposition to developers. Yeah, this is essentially a superposition. And the superposition was initially found like bullshit by Einstein and a few other of his friends. And one of his friends, the Einstein's friends that found this like bullshit, was the famous guy Ada. I mean, if they told me about Ada before, I would have put a picture of the cat here instead of just finding a clip art. So essentially, this is the fact. So the Schrödinger, another Nobel Prize for physics, Schrödinger created the paradox that, okay, if you, Mr. Bohr, are right about your idea that there are multiple states at the same time, it means that if I put a cat into a box with some poison, and of course I ensure that the cat cannot, take the poison. So the poison is in the box, but the cat cannot interact with it. So I have 2 distinct things: poison and cat. Of course, the cat can get the poison, but not necessarily. I mean, 2 states, poison and cat, into the box. Only when I open up the box, according to the physics, the quantum physics, only when I open up the box, I see the cat can be live or can be dead, depending on whether he got the poison or not. So he said, to try to make it paradoxical, so when I have the box with a cat and a poison, I know the cat can be at the same time live and dead. So that's the paradox that was done. But this is the concept of superposition. So now, to cut a long story short, today we have logical gates and or XOR and so forth that only work with 0 or 1, with a bidimensional mathematics. With quantum computing, we have vectors. Instead of 1, 0 or 1, we have just vectors. So the logical gates will be doing the same stuff, or XOR and whatever, but using vectors and producing matrices instead of just numbers. Quantum computers, multiple values at the same time. Process values simultaneously, but only when we read values, we break parallelism and we decide, we open up the box and see if the cat is dead or alive. But until then, the cat can be considered algorithmically both dead and alive, which enables us to write algorithms that are essentially naturally parallel. So it's a parallelism that is not achieved via hardware and more and more and more cores, but is natural in the programming model. So I don't know about you, but when I was at university, in some of the exams that I took about algorithms, parallel algorithms in particular, we were only doing theoretical exercises, assuming to have a machine able to run those algorithms. And we essentially were driven to figure out that any problem can be solved in a polynomial time if you have endless computing power. So if you can, in front of a decision, can spin up as many copies of the algorithm as you need. You have 10 options, you fire up 10 automatas that go ahead, and then for every other decision, are there 10, 10, 10, so you build a tree that potentially is endless. And if you calculate then the size, the computational size of going through all those paths, we have a function that is an exponential function. So that has the variable of the size as the exponent, which makes that inherently an intractable problem. If we find a way to deal with this, so if we find a way to do natural parallel programming without adding hardware and hardware and hardware, with one CPU, we can do parallel. We have essentially not an endless parallelism, but a significantly natural form of parallelism in one CPU, core, whatever it is. By having multiple of them, we can reach, potentially, theoretically, we can unleash a computing power that is immense. Interacting qubits can process information in a fraction of the time it would take a non-quantum system to do. This is, in a way, the idea of the structure of a quantum computing. This is the crude, in a way, of quantum computing. We have the problem of storing somewhere subatomic particles, finding a way to assign them a state, reading the state, and moving and updating their state. Crude, more or less. The fundamental operations in quantum computing, how we store qubits, how we give a state to qubits, how we move them in another state, and how we read the state back. These are the challenges. Now, how we could store in a quantum computing particles. The information here on this slide is just one way that companies are exploring. I could be wrong, but I don't think, for example, that Microsoft, in their announcement at the recent Ignite conference in, when was that? Was September, I think, they published a lot of information, but reading through that papers, it seems that they are not using in their prototypes this approach. But this is another approach that can be taken, and it's based on photons. So the qubit could be stored as a photon in between two extremely tiny mirrors. And a laser will be used to alter and to move the state of the photon across, okay, all those possible values. There are a few ways to store atoms and changing their states. This is, in my humble opinion, for the little piece of information I could have massaged in my mind, this looks to be the most promising, but it's not the only one. Concretely, according to IBM and their Q program, more information here, they had available to customers in this IBM-Q program a 20 qubit machine. And they have a prototype now, as we speak, with 50 qubits. But the interesting thing is that they went from 5 to 50 qubits in a little bit more than a year. So it's immense. So if the Moore law, some sort of that, could really be applied to quantum computing, maybe in 10 years, we can have available, maybe for incredible amount of money, but available, commercially available, quantum computers. Now, with a 50 qubit computer, we probably don't do much in terms of calculation. Why? Qubits are unstable because of the quantum, the tunnel effect. They are unstable, and there is something called the coherence time that is the metrics used to measure the stability and the reliability of the information we have. So, and on this point, both IBM, Google, and Microsoft, of course, agree that the most challenging point is doing error correction in low-level operations because of the way and the physics of the particles that so nothing is certain to be 0 or 1. It can be anything. So fixing errors, error correction is the most challenging part of the story. Now, the coherence time is defined as the average length a qubit will stay in superposition before it collapses to either 1 or 0. And the funny thing is that the environment, the surroundings, can have an influence on that. Coherence time is also the time, the real time the processor has to work. And both the 20 and 50 qubit machines from IBM have a coherence time of 90 microseconds, which is more than 2 times than the predecessor. So the challenge is increasing the coherence time, the time in which the processor can really work, can really provide parallelism, so the time it stays in superposition, every qubit stays in superposition, so it has multiple states, so it is able to do multiple parallel computing. So the more we raise the coherence time, the more programming power computing power actually, we gain for performing tasks. This instead is the Microsoft vision of a computer, a quantum computer, and this is more or less the architecture they have built in software, in the emulator they provide along with the Q# Visual Studio extension. The interesting thing in this slide is that essentially, okay, this is the compilation process, this is the computer. So in the Microsoft vision, there is a standard computer that is the facade for a quantum computer. So this is essentially the guy who does the parallel job, but then to be really usable in Visual Studio, let me use this expression. So to be really usable, because the power of quantum computing is not user interface, okay? Is algorithms. So, but to write programs, we need user interface. We need other aspects. We need to communicate data, results, numbers. So the quantum computing machinery is just for algorithms. And in the Microsoft pragmatic vision, we need to have an interface computer, a control computer that fixes errors, and then the quantum computer. Nobody really knows when there will be a change in this supremacy, who is faster. Today we have 50 qubits versus billion bits. So today, March 2018, reasonably, the brute force logic we can put into conventional computers still wins by far over quantum computers and prototypes. But the power, the potential that we have here is immense. Immense, and these are 4 challenges. Error-tolerant computing, effective storage of atoms, cryogenic processors, because there is the temperature issue. Maybe in Minsk this is not a big deal, but in Spain, in Italy, it would be a lot more problematic, okay, to have a cryogenic processors that can do manipulations inherent to the storage of atoms, okay, at cryogenic temperatures. 180 centigrade is the barrier that has been set in science between what is a refrigerating, what is so what's the terminal tag? What is cryogenic and what is just refrigerating? All those things are tightly related to improvement in the technology in nanotechnologies. Now, the bomb. Okay, we're preparing for the bomb. The bomb. No, okay, I'm done. Okay, I'm done. The problem are, with all this incredible potential power, computing power, we could have intractable problems all of a sudden become tractable. Not sure if you are familiar with the class of problems P and NP, deterministic and non-deterministic problems. To cut a long story short, P problems are problems that can be solved using a polynomial computational effort. So an effort that can be measured through a polynomial function. NP is those problems that are only solvable through an exponential algorithm. Permutations, all permutations of a set of n numbers, the traveling salesman problems, and most of optimization problems, prime factorization. Why prime factorization? Because prime factorization is the foundation, is the theoretical foundation of, let me skip this, doesn't matter, is the foundation of modern cryptography. So a quantum computing potentially could break any sort of known cryptography, whatever that means, military, banking, financing, whatever. We could live all of a sudden in a cave, dinosaur-style world. But quantum computing has the power to break cryptography and to unrule the world, but it also has the power of solving once forever the problem of cryptography. Quantum cryptography is a field that is in discussion for at least 30 years. And you know that, you may know that in cryptography, the Vernam code, which is a variation of the, is essentially a one-time pad. So every time there is a communication, there is a new key to code the message with the same length as the message. So one-time pad as long as the message. That has been proved mathematically in 49 to be unbreakable. The problem is that to apply concretely a Vernam code approach to security today, we still have to communicate the key. And so the mathematical proof is, okay, one-time pad with key as long as the message exchanged over a secure channel. So it's recursive. It's a recursive definition. We are trying to define what is absolutely secure as long as we can transmit something that is secure. So again, it's a recursive definition, but that's the issue, over a secure channel. Well, quantum cryptography has apparently the power to make unnecessary. So it's the physics of quantum physics, details. There are meters Google for details, but apparently the physics of quantums can make this part, the need of exchanging the key, unnecessary. And at that point, standing this mathematical demonstrations with quantum computing, we can have unbreakable cryptography. Thank you very much for your time. Blinking, it's superposition.
Thank you very much, Dino. Now we have some questions for some time for post-quantum questions.
Wow. I can answer or not answer.
Yeah, that's true. You can ask and
you can ask or not. Are you asking or you're not asking?
Could you tell me how I can create Q-sharp program hello world?
No, I don't know. Ask Microsoft. I tried to do that myself. But no, actually, yeah. My understanding is that quantum computing is for algorithms. So there is no UI, there is no hello world, or at least not at the moment. Or you may have hello world in many different languages. We can make a lot of jokes. No, actually, I don't know.
So it's only computing?
I'm tempted to say yes. It's essentially algorithmical.
Okay, thanks.
you can have hello prime.
Yeah, so my question is, if we got modern, up-to-date computer, quantum of course, so what should we do with existing data? With
existing?
Existing data, yes, all over the world. Should we migrate, erase it, or? So we got bool, it's true, false?
Honestly, I think that the Microsoft approach, or at least based on the information that is public, that I could find at this time, Microsoft is taking a very pragmatic approach to the point. They say, okay, we need to have an interface computer that is a conventional computer, and then in the back we have some sort of graphical unit. In much the same way we have a graphical unit to improve in the internal architecture for graphical operations or mathematical operations, we possibly might have, or this is my vision at least, a quantum processor that is able to do certain operations with an endless level, or nearly endless level of parallelism, native in the physics of the internal physics of the power. So I expect that computers will look like regular computers, but they will be equipped with something inside, some box inside that could be that is a quantum processor. And in much the same way today we have many cores, but actually high-level languages don't hide completely, the cores from ourselves. I can have 8, 9, 10 cores, but just a few APIs, low-level APIs allow me to control that. In much the same way, I expect in the future that we could have a C# instructions, async await, or things like that, that are able to take advantage of the hardware, the quantum hardware in computers. So I don't expect computers to be different, so data is still data. The way in which we manipulate data to extract numbers could possibly be different. Okay?
Thanks.
All right, we have a question over there.
Yeah, thanks for presentation. And just, like a summary, of your presentation. What's your personal advice of whole presentation? Do we need to look closely to quantum programming Q-sharp and so on? And what do you consider?
No, I think, yeah, I think, honestly, I think that, when I had the idea, okay, in first place, you have to be curious. Curious dummies. So when I had the idea of arranging this presentation and the guys here, the committee, Ivan and other guys accepted this talk for this conference, I had two ways, two possible approaches. Just install on Visual Studio the emulator and going through the Q-sharp demos. I tried that, but I could hardly figure out what I was doing. So I preferred to try to learn myself as a curious dummy. Okay, let me learn the theory. But the theory, theory, quantum computing. So I started with a Microsoft white paper. What is quantum computing? I stopped after a few lines because, okay, why there is this sentence? And then I opened up a parenthesis and drilled down into that content. I reached the level of transistors. And that started giving me the sense of what is quantum computing, where the power could possibly be. So this theoretical, in a way inspirational presentation that has a little bit more of physics than code came out. So honestly, at the moment, without this background, maybe even deeper than this, it makes honestly little sense that you approach Q-sharp, you install the thing, because they are nonsense instructions, fundamentally. You need to learn a little bit more. But even, high-level stuff, so quantum, just the 3, 4, 5 important things about quantum physics, just to see what is, without the concept of superposition, which is explained, by the way, in the Microsoft documentation. So you find there a number of words that you have to put into context before you can try to play and experience the sense of quantum on Q-sharp.
All right. Unfortunately, we are out of time, but we have a few things to consider. Number one, we got a chat room on Telegram where we are gathering questions for an interview we are going to do with Dino right today. Secondly, he's not vanishing. So after the other talks,
I can be there or I cannot be there.
Yes, you can grab him or not to ask some questions. So let's give a warm round of applause and thanks to Dino.
Thank you, guys.